morning. My name is Jeff Dudukovich. I'm the physics bus teacher for Seminole County Public Schools. Come on, let me take you on a tour of my mobile classroom. Due to COVID restrictions and inclement weather, we've unfortunately had to move our class today inside the school. But normally, we would hold up to 16 students here. They'd work in pairs, and we have 8 lab stations that I've designed with vertical articulation in mind. In other words, because of my middle school and my high school background, I know what the end is, and so I built these lessons as a base for where I wanted them to be. So, for example, here they're learning about light reflection, and they actually get to use lasers. These stations, they're learning about refraction, and they actually use a protractor. Over here we have focal length, where they have to calculate focal length, and then last but not least, they actually get to build 2 different types of telescopes and compare them. Now, the safety rules are posted here, and they're also posted inside the bus, okay, or outside the bus. So the kids are very aware of what what the safety precautions are. Mainly because of COVID, I'm making sure that anything they touch there, they sanitize their hands first, and then afterwards as well. Again, we've had to move inside the school, so what you're going to see are segmented lessons, just trying to compensate for the fact that we've had to move inside and we can't actually do the lessons like we normally would. Thank you. Good morning, soon to be afternoon, ladies and gentlemen. My name is Mr. D, and I'm the physics bus teacher for Seminole County Public Schools. And the great thing about being in 4th grade is that next year you're going to be in 5th grade and you get to see us again. But then we're going to have 3 buses: the mechanics bus, the optics bus, and the electricity bus. Unfortunately, due to weather conditions and COVID and elements beyond our control, we had to bring it into a classroom instead of being in the bus. But that's okay, because next year you'll get to go into the buses. So it is our mission to visit all 37 elementary schools here in Seminole County and introduce you to physics. Now, why physics? Well, physics is the study of matter and energy. And it's our hope, because it's a fundamental science, that, one, you'll get really excited about it, and 2, when you get in middle school and high school, you'll take more science classes, STEM classes, and things like that. We're hoping that you'll be inspired enough to maybe become doctors and engineers, and scientists and mathematicians, okay? What I'm going to start off with is I'm going to do something really, really cool. I had a student come to me, probably my 2nd or 3rd year teaching high school science, and he says, "Hey, Mr. D, check this out. I've got an endo board. You guys ever seen what an endo board is?" No. All right, so check this out. Let me go ahead and turn this off. And here we go. This is an endo board. So, the student comes into my class. He says, "Mr. D, check this out. I've got an endo board." I said, "What is that?" He says, "Well, it's a balance board." And I said, "What do you do with it?" And he says, "Well, you balance on it. Let me show you." So we walked outside my classroom, and he steps on this thing and starts balancing. And I said, "Man, that's pretty cool. Let me try." Well, he made it look easy. So I hopped on it, and you can imagine what happened, right? What do you think happened? I balanced? You think I balanced on my first try?
No, you fell.
No, I fell. I fell miserably. I fell on my elbow right on the concrete. It was horrible. But, I'm a tough guy. I got right back up again, and again, and again. And after about my 8th or 9th try, I said, "Wait a second. I'm a science teacher. What's the physics behind it?" So I went back in my classroom, and I turned on my computer, and I did like all good students do, and I watched some YouTube videos. And as I watched the YouTube videos, I was able to figure out the physics behind it. So I'm going to go ahead and demonstrate this for you, okay? Now, we are going to be doing some hands-on activities today, guys. We're going to learn about sound or review sound. We're going to talk about gravity. We're going to talk about how to set up an experiment, and we'll do a few things on motion. So I just want you to keep in mind that as we put our hands on things, make sure you don't touch your hands until you use hand sanitizer, or touch your faces. Right? We don't want to transfer any germs to our face and get sick. Okay? So here we go. All right, drum roll, please. Can I have a drum roll, guys? Drum roll. All right, ready? All right, get set and go. Oh. There we go. Come on. Hey. Guys like my dance? Pretty cool dance. All right, so see if you guys can guess who I am. I'm going to get you, Spider-Man.
Green Goblin.
Green Goblin, very good. Green Goblin.
Green worm.
All right, so what'd you say?
She said a green worm.
The green worm. Okay. So, green goblin, I look like a green worm. That's great. Okay, so I'm not a green worm. So check it out. Here's the physics behind this. So as you guys have a good vantage point from here. My center of mass is right here. With other people, it might be here or here. Since my center of mass is here, as long as I keep my center of mass over that pipe, I'm not going to fall. Just like riding a horse or a motorcycle or a bike or maybe a big dog. As long as you keep your center of mass over it, you're good, right? You're not going to fall. So, but if your center of mass falls away, look what happens. Okay? So once I watched a couple people doing it on YouTube, I was able to figure out the physics behind it. So I could realistically say that physics saved my life because I could have kept on going and maybe fallen and cracked my head open, right?
Yeah.
That makes sense? Okay, so that's why physics is a beautiful thing. A good knowledge of physics helps you to explain what's happening in the world around you. Let me give you another example. So here I have a very large balloon. Would you mind helping me out? Could you hold this and just kind of stand up and stand right there? Okay, great. Fantastic. So I have this very large balloon, ladies and gentlemen. So question for you. I want to blow this balloon up. How long do you think it's going to take me to blow this balloon up?
5 seconds.
What do you think?
About 20 seconds.
About 20 seconds? I heard 5 seconds over here. What do you say?
7 seconds.
7 seconds? All right, anybody else?
8.
What do you think, 8? Okay, so we're talking in seconds, right?
A minute.
A minute? Okay, so let's find out. You guys ready? Okay, so you have one job to do. Don't let go. Don't make me look. Got it? All right, here we go. Ready? 1, 2, and 3. Oh, don't pull it. There we go. Perfect. Okay, so go ahead and let that go. Thank you very much. All right, ladies and gentlemen. So, as you can see, I blew that up in a very, very short period of time. Now, without a knowledge of physics, you could look at that and you could say, oh my gosh, it's like magic. Oh, how do you do that? But there's a logical explanation. So let's think about this for a second. You guys, I think we can all agree all that air didn't come from my lungs, right?
Yeah.
Okay, so I want you to think about this. Picture you're at the beach and you're digging a hole in very dry sand. What happens to the sand around it as you dig that hole in that very dry sand?
It keeps falling back in.
Right, it falls back in, right? It collapses. Well, the same thing happened here. When you really think about it, as I started to blow into the balloon, I created this current of air, and all the air around it just kind of fell right in. Okay, pretty cool, right? An explanation of physics. Okay, so we're going to segue into a little activity on sound. Okay, sound is vibrational energy. Now, I'm sure you guys are familiar with what these are, right?
What, metal chopsticks?
Metal chopsticks. That's exactly what they are. They're metal chopsticks. Okay, so ladies and gentlemen, these are tuning forks. Okay? Tuning forks are engineered to vibrate at certain frequencies to give off a certain pitch. For example, lower frequency vibrates more slowly, has a lower pitch. Be like the bass. Okay? Shorter, higher frequency vibrates much faster, has a higher pitch. I am going to demonstrate the difference in pitches in this balloon. So listen very carefully. Hear that? Hear the difference?
Yeah.
So what I'd like to do with you now is I want you to experience sound as vibrational energy in 3 different ways. I want you to see the vibrations, I want you to hear the vibrations, and last but not least, I want you to feel the vibrations. Hopefully you walk away with good vibrations, okay? And then I'm going to ask you a very important question. So, my partner, Mr. Medlock, and I are going to come around, and we want you to look at the end of the tuning forks. Go ahead and look at it. Can you see that vibration? See, it's kind of blurry, right? I know it's hard to, can't focus on it, right? Okay. Now that you've seen those vibrations, what I'd like you to do is I want you to listen to the vibrations. We come back around and just listen to the different.
Okay. That's so cool. It's cool. It's weird to hear it. I just got so scared. My ears are going to go bye-bye.
And it's really strange because you can't really hear them far away, but up close.
Oh,
Not that much. So now that you've gotten a chance to see the vibrations and hear the vibrations, I want you to feel the vibrations. Go ahead and put your palms out. And remember, Don't touch your faces until we give you hand sanitizer, okay? Here we go. Ready? Some people it tickles, some people it feels like a shock. Well, you're about to find out. All right. So, ladies and gentlemen, you got to experience sound as vibrational energy 3 different ways. Sound is vibrational energy. Now, if I did this same activity out in space, you'd be able to see the vibrations. You'd be able to feel the vibrations, but you would not be able to hear the vibrations. But why is that? Raise your hand and tell me. What do you think?
Because there's no air in space, and that means sound waves can't travel.
Are you trying to get my job? You're absolutely right. So there's no matter in space. We need that matter. Sound requires that matter to transfer that vibrational energy. Without matter, which is either a solid, liquid, or gas, you can't transfer it. In physics, we call that a medium. Okay, so if there's no medium in space, well, obviously that sound energy cannot transfer. Okay, now that we've talked about that, very good answer, by the way. What I want to do now is I want to show you what sound waves actually look like. Okay, so I'm going to need volunteer. You look like a great volunteer. Here we go. What I'd like you to do is I want you to hold that much of the slinky. Okay, and I want you to come over here and I want you to kneel down and hold the slinky down close to the ground. Okay. Hold it close to the ground like this. So, ladies and gentlemen, as I am speaking to you, my vocal cords are vibrating, and they, of course, are transferring that vibrational energy through the air molecules until they reach your eardrums. And, of course, your eardrums start to vibrate, right? Those vibrations are transformed into electrical impulses that your brain translates as sound. This, if you can hold it down, there you go. This is what a sound wave actually looks like. Okay? This is called... It's called a, where's my vocab? Here we go. It's called a compression wave, okay? It's a compression wave. So, you can see that I'm compressing, pushing and pulling. Compression wave. So this would be a low frequency bass, boom, 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 boom. Okay? This would be high frequency, high pitch. Okay? So, low frequency, high frequency. And that's what's happening to the air molecule. All right? Outstanding. Thank you guys so much. Go ahead and let that go. Gravity. I normally don't like to talk about gravity because, well, gravity always brings me down. But I have to because it's a standard you guys need to know about. Ah, you got that dad joke, right? All right, so in front of me here I'm holding 2 spheres. Okay? They take up the same space, so that means they have the same... volume. They have the same volume. That's right. I always forget I'm old, so I forget my vocabulary. So they have the same volume, right? But this one is obviously a metal ball. This one is a hollow ping pong ball. So I know this one has more, somebody already said it, mass. It has more mass, right? So since they have the same volume, but this one has more mass, I can say this one is more dense. It's got more matter packed into it. Okay? Now, I've heard it said that heavier objects fall faster. Okay? I don't know whether or not you agree with that, but I want to put that to the test. So, let's go ahead and find out if heavier objects do fall faster. All right, so here we go, guys. You ready? So, if I'm going to do this experiment, how many times should I drop these balls?
1.
No.
At least?
5.
Who said that? At least 3 times. At least 3 times, guys. 5 would be great if I have time. 3's a good number. Okay, ready? Remember, guys, don't touch your faces until we get you some hand sanitizer. Here we go. You ready? Okay, 1, 2, and 3.
No.
Looks like the ping pong ball wins. What's wrong?
You dropped the heavier one this high and you dropped the other one. You dropped it.
Well, wait a second. It's my experiment. Shouldn't I be able to do it the way I want to?
No.
Right, you're right. You're right. Because that's an additional variable that's going to affect the outcome, right? I don't want that. I only want to test one variable, not 3. 4 or 5. So here we go. You're right. Good job. So here we go. So same height, right?
Yeah.
Okay. 1, You gotta pick your class here. So wait a minute. What are you saying?
You're dropping one ball and then the other.
So I need to drop them from the same height at the same time?
Yes.
Okay, good. And you guys are right. So that's going to allow me to just test one variable. Which one's going to hit the ground first? Same height, same time. So all the conditions being equal. Here we go. Ready? Same time, same time, same time.
Same.
Wow. Same time. But I don't know if my results are valid yet, so it's very important that I have another scientist or person come and test that the same way. So they need to replicate it. So they're going to replicate it. Okay? So would you mind coming up and replicating it for me?
Me?
Yep, absolutely. So there's a lot of pressure here because, they're very picky. So same height, same time. All right, so we're going to do 3 times, right?
You ready?
Yeah.
Oh, that's 1,
1 millisecond.
2,
1
Yeah, by a millisecond.
and 3. Outstanding. All right. All right. So not only did he do it the right way, but he followed my procedure, got the same result. So now I know I have a valid experiment. But I don't know if I'm happy with just testing this against a ping pong ball. Okay, so I think I'm going to try testing this against some other things. So now this is my control, guys. This is the thing that I am not going to change. Okay, it stays constant. I'm going to compare everything else to it. So let's try baseball. Okay, you guys ready? Oh, same time. Now normally I would do this 3 times. Okay, so they land at the same time. How about a ball pit ball? Same time. Same time. Same time. What about this styrofoam brick? Same time. Whoops. Try to get away from me. Same time. And same time. Oh. So guess what I just did? I just showed you that the force of gravity acting on you and you and you and this is the same regardless of the mass. So heavier objects do not fall faster, guys. Okay? It's a very important concept to understand. I've seen, sometimes kids learn that the wrong way and they get into middle school and high school and I'm trying to teach them about gravity and they don't believe it. They don't believe what they see. So now you guys have the proof right there. But watch this. You ready? If you didn't see it, you heard it. They didn't land at the same time, did they? So what slowed that brick down? What did you think happened?
Since it's so it's like a glide suit and it's so wide that the air
Glide suit. So it's wide like a glide suit. So what did it do? It captured.
It captured the air.
Okay.
And it didn't fall.
Okay, what's another example of something that slows down in the air?
Gravity.
No, not gravity. What's something else that slows down in the air that you can think of?
Paper.
Paper, parachute, right? So it acted like a parachute, right? Because it's got a larger surface area. It encountered some air resistance. So that's what slowed it down. Now, I want you to think about this. If you have mass, you have gravity. Okay? If you have mass, you have gravity. So even a little speck of dust has some gravity. It's got mass, right? So if I went to the moon, because the moon has mass, it's got gravity, right? If I went to the moon and I did this same experiment on the moon, how many of you think this would land first? Who thinks this would land first? Who thinks they'd land at the same time? Okay. Who's not sure? Who thinks I'm trying to trick them again? Okay. I'm not trying to trick you. I'm trying to teach you. I'm not the tricker. I'm the teacher. Okay, so check this out. What does the Earth have that the moon doesn't have? I'm going to give you a clue. Yes.
Gravity.
Well, it's got gravity. I just told you. If it's got mass, it's got gravity, right?
Air.
Air. That's right. So the moon doesn't have an atmosphere. So what slowed this down?
Air.
Air. If the moon doesn't have it, is something going to slow it down? So it's going to fall at the same rate and land at the same time as this golf ball. There's an experiment where an astronaut took a feather and a hammer and dropped them on the moon from the same height at the same time, and they landed at the same time. You guys should check that out. Okay? So, heavier objects do not fall faster. All right, now we're going to go to part 2 of gravity. All right, so here's what I'm going to have you guys do. It's a very large class. I'm going to have you right where you're at. I want you to come and I want you to form a circle around here, but about at least 3 feet away. I want to make sure that nobody is blocked out. As I mentioned earlier, if you have mass, you have gravity. So if 2 of you were out in space and there was nothing else around, no stars, no planets, no galaxies existed, just the 2 of you, this is what would happen to you. You would come together no matter where you were at. Okay? You're going to eventually come together. And think of this as the fabric of space-time. Now, Those are two high mass balls. Let's take a high mass and low mass and let's see what happens. Notice it takes a little bit longer for them to come together, right? They still come together, you're right. It just takes a little bit longer. So, I'm going to ask you a question. Guys, here's where we get into 8th grade material. I know you guys are going to get this. Is gravity stronger between these two, based on what you saw? Is it stronger between these two or between these two? How many say the first two? Raise your hand if you think the first two. How many of you think the second? Okay, very good. So, it's these because they have more mass. So gravity depends on the mass of two objects. It also depends on distance. So is gravity stronger here or here?
Yeah.
How many of you think the first one? Raise your hand. Who thinks far away? Raise your hand. You didn't raise your hand. Why not? Because you don't want to? Okay, that's fine. That's fine. All right, so the answer is the closer objects are, the stronger their gravitational pull. So gravity depends on two things, the mass and the distance. Guys, that's 8th grade stuff, and you're already 4th grade? Get out of here. That is awesome. Okay, now, I want to teach you guys something this is really cool. And then we're going to build a model of the solar system. And if you want to build this for the school, I can take a picture of this, email me, and then I'll send you plans, and you can do that, okay? So check this out. It's a gravity well. You can find it out online, but in space, we have these giant clouds of dust and gas called nebulae. They're so huge, in fact, that you could fit many, many solar systems in them. In fact, they say that they're the birthplace of stars. So the theory goes that because dust and gas have mass, they have gravity, over time, these massive amounts of dust and gas start to come together or accrete. And look at this, ladies and gentlemen. We have a baby star. How cute. Right? There's a baby star right there. Oh my goodness. Now, which do you think is more massive? This massive ball or all those marbles together? Okay. Let's find out. Let's find out. Ready?
Cool.
So look at that. That larger one was so massive it actually flung those particles out into orbit. Pretty crazy, right? Okay. So now let's build our solar system. So let's put a star in the center. Okay, let's give it more mass. This is 4-way spandex. So if you want to build one of these at home, it's actually pretty easy to do. Okay, so there we go. We've got enough mass in there. So that's a very massive star. Okay, we don't have green stars. We have red, white, blue, and yellow stars. But anyway, that'll suffice. So, what do you call the path that a planet takes around a star? An orbit. And there's another word for it. Starts with an R. Not rotation. Oh, somebody took my... Rotation is when it spins on its axis, right? Revolution. Very good. Revolution. So, they're revolving. Now watch this. This is an amazing thing. Pretty neat. Thank you. I'm going to take this low mass ball. I'm going to roll it with these marbles. I want you to watch the interaction. Notice that the marbles don't really affect it. It doesn't really affect the marbles, right? It's got a very low mass. So I would expect its gravity not to be very powerful. Now, hand that one. Thank you. You did a great job. Thank you so much for holding it. All right, here we go. Watch this. Ready? Look at what's happening now. They're orbiting around that one. Okay? And if I roll it again so you guys can see, watch this. See how they kind of stick together?
Yeah.
Okay, like moons. So that's why Jupiter has so many moons, guys. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, are very large, massive gas giants. So because they have more mass, they attract more debris and things, and that's why they have so many moons. Okay? So you kind of think of them as the solar system's vacuum cleaners. They protect all the smaller inner planets. Okay? Does that make sense to you guys?
Yes.
Okay, outstanding. So, pretty cool stuff, right? That's gravity. Thank you.